Welcome to the lecture series on PN Junction Diode. In today's lecture, we are going to discuss about the diode resistance. Ideally, diode is supposed to offer zero resistance in forward bias and infinite resistance in reverse bias. However, for practical diode, the forward bias, here we get very low resistance, very low resistance, and here we get very high resistance. Now the forward resistance, we have static resistance or DC resistance, dynamic resistance or AC resistance, and an extension of this dynamic resistance is average AC resistance. Now let us have a look elaborately. So static resistance, we can find some instantaneous point and we can project the value of voltage and current corresponding to this point. So here we are analyzing the forward bias characteristics and finding the static resistance at a given instant. So the forward bias resistance, which is denoted as R, capital RD or capital RF, and it is given as VD by ID. However, this increase is exponential. The variation of current with respect to voltage is exponential. So for linear variation, this kind of approach may be good. However, for exponential rise, this may not be a good way of finding the resistance in forward bias. Similarly, we have resistance in the reverse bias and it is calculated as the reverse voltage divided by reverse saturation current. Now we know that reverse saturation current, it is in terms of microampere. So as a result of that, we get the value of the reverse resistance very high. Similarly, here we get the forward resistance very low. Now further have a look at the forward resistance. So here we have this as the dynamic resistance. How do we calculate it? Similarly, just like our calculation of the static resistance, here also we take the similar approach. Only thing is that instead of finding this I and this V, what we are finding, we are taking a tangent, and in that tangent we are finding VD and ID. So this is basically providing us the change in the forward current with respect to the change in the forward voltage. So whatever voltage change is taking place, with respect to that, how much current is changing. So that is why we are calling this as the dynamic resistance. So dynamic resistance, which is denoted as RF or RD. So here you see that small r is used in case of dynamic. In case of static, we have used capital R. So it is given as delta VD by delta ID, or we can write it as dVD by dID. So change in voltage and change in current. However, many a times finding this instantaneous point is little difficult. So instead of that, we sometimes consider a range over which this dynamic resistance is calculated. So we call this as the average AC resistance. So expression wise, if you look here, it is same as that of the dynamic resistance. However, the definition of del VD and del ID has changed here. So here we are not considering a single point, rather we are considering a range of voltage and range of current. So over a range of voltage, whatever is the change in the range of current, that is what we are finding here, and their relation is giving us the average dynamic resistance or average AC resistance. Now let us try to find the mathematical expression associated with the dynamic resistance. So let us start with the diode current equation. So this is a very familiar equation for us. So I, which is our diode current, so here we have denoted it as ID. So same thing here we have I, and IS is the reverse saturation current into exponential or e to the power Vd divided by eta Vt. So Vd is the voltage across the diode, Vt is the thermal voltage, and eta is called the ideality factor, and we know that eta is given as 1 for germanium diode and it is 2 for silicon diode. Now you see here this equation we can rearrange and we can write it as I equal to Is e to the power Vd by eta Vt minus Is. So if we take Is to the other side, we can write I plus Is, that is equal to Is e to the power Vd divided by eta Vt. So let us call it equation number 2. Now our objective is to find the dynamic resistance, and we have seen that dynamic resistance means we need to find the change in voltage and change in current. So to find that change, we need to differentiate equation 1. So we have differentiated the equation 1 with respect to Vd. So we can write d dVd, that is for Is e to the power Vd eta Vt minus 1, and if we rearrange it, we can write it like this. However, d dVd of 1 is a constant, so we can write it as 0. So we are getting it as Is d dVd e power Vd divided by eta Vt. Now here this is as same as this. So since d dx e to the power x by a is equal to 1 by a e to the power x by a. So applying the same concept here, we can write it as di by dvd, that is equal to Is eta Vt into e power Vd divided by eta Vt. So this thing we are getting after differentiating equation number 1. So let us call this relation as equation 3. So now dynamic resistance is given as dVd by di. So in previous case, equation 3, we have found di by dVd. So practically Rf is the reciprocal of di by dVd. So whatever we have found in equation 3, we are substituting that value over here. So we are writing it as Is divided by eta Vt into e to the power Vd divided by eta Vt. So if we are taking this to the numerator, so we can write Rf is equal to eta Vt divided by Is e to the power Vd by eta Vt. So now if we have the knowledge of Is and the knowledge of Vd, that means voltage across the diode and the reverse saturation current, if these two information we have, then we can find the dynamic resistance with the help of equation 4. However, if Vd is unknown and the current across the diode is known, then by utilizing this relation which we have found in equation 2, so we can replace this Is e to the power Vd by eta Vt. This thing we can replace by I plus Ia. So equation 4 we can rewrite as Rf is equal to eta Vt divided by I plus Is. So if the current through the diode is known to us, reverse saturation current is known to us, this value under room temperature we know, we can consider it as 26 millivolt. Some cases we consider it as 25 millivolts also. And eta value we already know, 1 for germanium, 2 for silicon. So we can find the dynamic resistance. And in case of the diode current, if we are given the value of the voltage across the diode, then we shall utilize the equation 4. So these are the two expressions to find the dynamic resistance of a diode. So here we end this discussion. Thank you and join me for the next lecture.